Hey, welcome back to Fat Mama Physics. Here we have examples on conservation of momentum, which in these examples we will be dealing with collisions. I do example 1, you do example 2. Let's get the show on the road. Whenever you're dealing with collision problems, it's good to draw a before and after picture. So let's read the question first. A 0.25 kilogram cue ball, I'll label this mass 1, is traveling east at 4.5 meters per second. So I'm going to write that's our velocity of our number 1 mass when it collides head on with a 0.25 kilogram 8 ball. Okay, so that's technically the same mass. I'll call it mass 2, traveling west at 5 meters per second, second velocity there. After the collision, the cue ball, that's mass 1, is traveling west at 2 meters per second, so that's V. Okay, so there's an initial and a final. So I'm going to do this U here for initial, and this same here. Same thing and final with VI. What is the final velocity of the 8 ball? So that's V2, and that's U, just to show that there. Okay, so we got two masses. They will collide. There's a before and after. So let's draw a picture first. So here I have the before picture. The cue ball is traveling 4.5 meters per second to the east, and I'm going to label the east as my positive direction. So then if my mass 2, which is the 8 ball, is traveling west, this is going to be a negative velocity. So I'm going to write the U2 for the initial velocity of the second ball is negative 5 meters per second. Okay, so a negative sign right there. Now, after the collision, the cue ball is now traveling west. So the cue ball kind of bounces backwards, which means its final velocity is now negative in the negative direction, which I will write as negative 2 meters per second. We don't know what the 8 cue ball is doing. Let's just say it goes backwards in the diagram just for show's sake. And that's the velocity that we want to find. Okay, so using our conservation momentum equation that we derived in the previous video, so let's write that down. And in this case, we want to solve for the final velocity of the second mass over here. So I'm going to go ahead and do some algebra to solve for V2. First, we need to move M1, V1 to the other side. Next up, we're going to divide the whole other side by mass of number 2, M2. Now we're going to plug in all of our values into our equation, and the key thing in this step is making sure you plug in the correct signs for your velocities. Okay, so notice that the initial velocity of the cue ball was positive because it was going west, and that's the positive direction. The 8 ball, mass 2, was traveling west, that's in the negative direction, and then after the collision, that is velocity 1 of the cue ball is going backwards west, so that's a negative 2 meters per second, all of that divided by the mass of the second ball, which is the 8 ball. Now, if you had canceled out your mass already in a previous step, great job, because the mass, luckily, is the same for both objects. So absolutely, you could have just dealt with the velocities here instead of the including the mass. But let's go ahead and calculate this out. And here we get 1.5, and it's a positive value, which means this is 1.5 in the east direction. Just to make sure that, don't forget there's a negative sign there, that's also a negative sign, which then would cancel if you're putting into the calculator. And the key thing when you're answering a momentum question is to include the directions with your velocity. That is very important right here. Okay, so that was the first question. You are in charge of doing question number 2. And I will put the solutions on fast play. If you want to here, we can go over it. We can go over the question itself. A 1,500 kilogram. Oh, it doesn't say what it is. Let's say it's a car. It's a car, and it was traveling south, hey, don't forget this is kilometers per hour, hint hint, when a 4,500 kilogram truck rams into the car from behind, also going south at 70 kilometers per hour, after sticking together, what is their final velocity after the incident? What kind of collision was this one? So we can, first of all, let's ignore this second half of this question. We haven't done that yet. We will talk about that later. But they do stick together after the collision. So if I were to draw a picture, here's a car and the truck. They're stuck together. Okay, I'm going to leave it as that. So they are sticking together at this point. And if they're sticking together, they are moving together. If they are moving together, what does that tell you about their velocities? Hint, hint. Okay, so now I hope you have enough to at least try this problem. I highly encourage you to draw a before and after picture before you try to tackle the problem. Okay, don't forget your directions, positive and negatives. I wish you good luck. Good time to pause the video, and we'll see you back. Alright, now it's my turn to do the solutions. So we're going to draw the before and after diagram of the collision of these carts. So I'm going to label cart as C, truck as T for their masses and velocities respectively. And going south, we're going to label that as the positive direction. So then I kind of just screwed up. You got to make sure you read your problem. The car actually gets crashed in by the truck. The truck's coming in from behind, going at 70 kilometers per hour, crashing into the car, and the diagram had to modify accordingly. But since they're traveling together, they have the same final velocity, which then I just wrote they were equal. And here we should actually convert their kilometers per hour to meters per seconds. And if we were to do that, the shortcut is to divide by 3.6. I'm not going to do that there because I could just put that into my equation. And in my equation, I have the mass of the car and its initial velocity plus the truck's initial momentum equals to their final momentum. And since they're traveling together, the masses I can add together times their final velocity. Dividing by the sum of their masses on both sides, I isolate for that velocity. I can put in my values, in which I could just take their velocity, kilometers per hour, divide by 3.6 there. And then on the bottom, I divide by their combined masses. Now it's time to calculate. And this is something you got to be very careful. Make sure you put some extra brackets, which I did a mistake here, and I realized that. So I went back to calculate again, step by step. So don't forget, when you're doing this, make sure to put in brackets in your calculator. So here we get 18 meters per second, and it's positive, so it goes to the south. Alright, and here are the solutions to this problem. So in fact, I drew the picture wrong to begin with. In fact, the truck was coming from behind and rear-ending the car in front, both of them going south. So hey, there were no negative signs you had to deal with. All of them was positive. The other thing I want us to notice is the fact that when the two cars are sticking together in the end, if you said their velocities are the same, you are correct. So that was the key thing here. If things are sticking together, they're moving together, therefore having the same speed. So I just use V instead of the individual VC and the VT for car and truck. And in the end, I was able to factor out a V out of these two terms. So factoring out of the V, we get MC plus MT inside. We can just divide both sides of the equation by the combined mass of the car and the truck. When I put in the values, I used meters per second. So I showed this over here, which in order to get meters per seconds, in the previous video, a few videos ago, I showed us how to get meters per seconds just by dividing by 3.6 instead of having to do the long conversion. So instead of calculating it out, I got a little bit lazy. I just put it directly inside my equation there to show that we are using meters per seconds. Now, if you were super savvy, you could have just left your answer in kilometers per hour, and your velocity in the end would turn up to be kilometers per hour, since the conversion rate would be the same for every single term in your equation. However, if the question does ask you for the velocity in meters per second, don't forget to convert it in the end if you've done that. Also, be very careful when you are putting in your numbers into your calculator. Don't forget to include as many brackets as you can, including the top here. If you do put everything in your calculator, don't forget to bracket the top all together before dividing by the bottom. The bottom, which also should be bracketed as well. So be very careful with using your calculator. And at the end, we get a positive number. And even though it says positive, make sure you include directions, which from the question, we chose south to be our positive direction. So I put south for my directions. Okay, so hopefully this video answers some of your questions, gives you some tools, and also catches some of the mistakes you can make during a problem. I wish you good luck. I thank you for watching this video, and Fat Mama Physics signing out.